Is this here? Okay. Before I want to talk about what Shray is exactly, I would like to motivate why we need Shray. So when doing scientific computations like solving differential equations, that kind of stuff, these are often very fast algorithms like linear or n log n. And before the time runs out, you're probably going to run into an issue where you just do not have the memory in order to make your computation precise enough. So I've done a few numbers on the machine we have at Radboud, just to give you an idea about the kind of time you have. So if you fill up this 128 gigabyte machine to its entirety and do a full multi-grid method, which is for PDEs, it takes less than a minute. And even for Fourier transforms, it's a few minutes. And you may have a number of these primitives in your simulation, but still, if you start the simulation when you go home, then the next day you will have your results. So there's a limit to the amount of memory we can put in a single computer. So the way people solve this is by taking a bunch of computers and then connecting them to a network so that they can pull together both their computing resources as well as the memory. This is pretty hard to program because you have to take care of data placement explicitly, of communication explicitly. So kind of the dream is that we have some kind of array language that is close to the math, and then the compiler will take care of creating an efficient distributed program for you. So the semantic gap is obviously very big here. So what Shray aims to do is to sit between this and kind of abstract over the distributed memory. So Shray is a form of DSM, of distributed shared memory, which means that it imitates shared memory over a distributed system. But instead of doing this for the entire computer, like in classical DSM systems, it does it only for specific arrays. So when you allocate a piece of memory, you can say whether you want this to be replicated on each node or whether you want this to be distributed. And there's also a owner compute restriction, which means that we have a concept of ownerships. I will go into detail later. And only that node is allowed to write to it. And that allows for a efficient and simple implementation. And I will argue that that is good enough for numerical codes that these kind of array languages target. Well, I think at the open mic I already told this a little bit, but the implementation is pretty rudimentary at the moment. So I will focus in this talk on the main design ideas and not the exact implementation. So I want to introduce a motivating example to kind of give you an idea on the kind of problems we solve. So there are iterative methods that consist out of multiplying a matrix with a vector repeatedly. And often these matrices have a lot of zeros, which means that it would be a waste to store these and multiply by these zeros explicitly. So a matrix with a lot of zeros is called a sparse matrix, and you have an example here. So the color thingies are non-zeros, and the rest is all zero. And we store this as three arrays. We have the values in just a linear one-dimensional array, the corresponding column indices. And then we also need to know which values belong to a row. Because if you compute a matrix vector product, then you take one row of this matrix and take the dot product with a vector. So that is why we have this row boundary array over there that shows the first and the last element of each row. So in SAC, which is an array language, it looks something like this. And then for a single node, it's not hard to generate the code. It's pretty straightforward. Your map thing becomes a loop, so that's the outer loop you see there. You can parallelize this. And then we have an inner loop that sums up the values, which is the reduction, the sum in the middle. However, for distributed computing, this becomes a lot more difficult because we need to know where the data is stored, and we need to have some kind of correspondence between the global data structure we know exists and what actually is in the memory. So if we would like to generate explicit MPI code, then we would have to first conceptually divide the array into pieces. So say we have 3 nodes, then we'd say, okay, conceptually we have something like this, and each node is responsible for computing one of these 3 parts. And then in the actual code, each node just has one smaller array and an identifier, which is like 0, 1, 2, etc., that says which node it is. And we can then make a correspondence between our local indices of this thing and the global indices of the entire array. So in this case, you would multiply your identifier by the number of elements in one of these blocks and then add your local index in order to get the global index. So that means that we would get something ugly like this code. The outer loop is still fine. It just loops over a restricted range. But on the inside, we have to compute for every axis on which node the data lives and what the local axis is, local index is. So then we get, for example, this local check, and if it's not, then we have to compute nodes, call MPI on it, and then sum the array. So this is both quite ugly and quite expensive because we have all of these explicit MPI calls in the inner loop. So we decided to not do this. So the main problem with DSM is that you have to take care of memory coherency. So if there are multiple, if your data exists in multiple places, you need to know who has the valid copy. And like we just saw, the reading is difficult, but the writing is not. Like if you define functions or vectors, you usually define them pointwise. You say f I comma j is equal to something. So we have control over the writes, but not the reads. So we just say, okay, if you have the element on your node, then you're the only one who's allowed to write to it. And that makes the memory coherency trivial because the node with the valid copy is the one that owns it. So instead of having one local data structure, in Shray we just allocate the entire thing in virtual memory and make sure that only part of this actually exists in physical memory. So if you're node 0, then there are 2 helper functions, Shray start and Shray end, that tell you what part of the array belongs to you. And depending on which node you are, you get different pointers here. So that way you can keep track of what you need to compute. And that means that for parallelizing this code, you don't have to touch the inside of the loop. The only thing you need to do is you have to tell Shray that you want to parallelize, that you want to distribute your array. So that is this Shray malloc thing. The first element is the size, the first argument is the size of the first dimension. So in this case it's just n, but if we have an m by n matrix, you may choose m there. And then we restrict the range to Shray start and Shray end. And then if we want to use this array after, we need to make sure that all nodes have finished computing before we start reading. So that is why there's this Shray sync function that is more or less a barrier synchronization. So there are things you can do to optimize this MPI version I showed you first by doing some static analysis, but this is pretty brittle. So we have done some benchmarks. Here I've presented the results for 3 languages. UPC and Chapel take kind of the MPI explicit approach by inserting communication primitives. And Shray does this all at runtime. This is a conjugate gradient method which uses the sparse matrix vector multiplication of the example as main computational kernel. And you can see that as soon as we go out of node, so between the 1 and the 2 we use 2 physical machines, that we get a huge drop in performance. Also for Shray, because this is a very small example. But you can see this logarithmic scale, so there's like a factor 100 between it. So explicit communication can work well because you have less overheads, but it's pretty brittle for performance. So on the technical side, the basic idea is that we rely on segfolds. So the grayed out part is part of the memory that you are not allowed to read or write to. And the black part is the memory that you own. And you do have full read-write access there. So you can just do your normal thing. You can pass this memory to an external library if you so wish. And as soon as we hit, for example, this data access at node 0, then this will raise a segfold. And we can catch that and make sure that we communicate the data from the correct node to that position. This works in a cache manner, like a cache, because we don't want to have too much physical memory at each node. So after a certain runtime configurable amount of memory has been used, then we unmap parts that we fetch from other nodes. So if we have to read that again, we would have to communicate this again as well. And yeah, there are some more technical stuff, but this is the main idea behind the implementation. So in order to make distributed programs perform well, we need to make sure that the synchronization is cheap, but that kind of trivially holds because of this owner compute rule. We need to minimize the amount of data communicated, but I feel like this is more a property of the algorithm rather than the actual Shray library. For example, like a blocked matrix multiplication on CPU is made so that the data access is good and that you do not have to communicate too much between RAM and CPU caches. And that same idea will also hold for Shray. And then finally, we have to mitigate the latency of fetching elements, and that is important to handle within Shray. So we have basically two complementary strategies of dealing with this. So naively, your communication pattern might look something like this. So we segfold, then we have to do some Shray overhead, like computing where do we get the data from. Then we have to wait for the data to arrive. That is all the red part. And only then does the data start coming in and we can do something with it. So that is the green thing. And you can see there's a lot of red, so there's a lot of overhead. So a simple thing, just like hardware caches solve with cache lines, is to not fetch one element at a time, but to fetch multiple elements at a time, so you can spread out this latency hit over more data. We have a runtime environment variable that you can set for this Shray cache line. And for many applications like a matrix multiplication, a stencil, a blocked and body implementation, this is enough to reduce the latency to almost nothing, because you can fetch a megabyte at a time or even more. And because all of these algorithms are optimized for CPU caches, this carries over to Shray. So we can profile the amount of data communicated. And for matrix multiplication, we see that it is actually the minimum amount. That's only communicates like 3% more than a handwritten explicit communication version does. So this works fine in cases where we have good temporal and spatial locality. But for things like conjugate gradients, sparse matrix vector multiplication, your data accesses jump all over the place. So if you take a large contiguous block, then you're just communicating in a bunch of junk, and that unnecessarily stresses your bandwidth. And also it doesn't really help with the latency. So instead we encourage people to use multi-threading in their code. It is completely thread safe, Shray. So they can segfold and communicate data at the same time. And that way we kind of overlap the latency penalty, because your T threads can segfault at the same time, and then they can fetch one page at a time. And that way we do not have to put in a bunch of junk. This never hurts, but we are limited by the number of threads. Like if you have 8 threads, then you can cut the latency by at most a factor of 8. So in some cases this may not be enough, but it seems to perform decently. So this is the same benchmark I showed in the first picture with the large performance drop, but on a much larger data set. On the right-hand side, we have the figures for Shray. This uses the OpenMP version from the NASA benchmarks, and then I just threw in the Shray malloc on the allocations and hit the loops. And the MPI version is also from NASA, but that does not use OpenMP, unfortunately. So that is why you see that at the start, Shray is a bit faster. And here you can see that going from 1 to 2 nodes, we get some speed up. Afterwards, our speed goes down a little bit. That is because we have a very poor interconnect on this machine. It's just a 1 gigabit switch that all the nodes are hooked up on. So MPI is able to get better performance because it can, so conjugate gradient does a sparse matrix vector multiplication multiple times. So what you can do is you can analyze the communication pattern and communicate only exactly what you need on each call afterwards. And we can do that in Shray, but we still get within a factor 2. And it is also scalable. So I think that is a very decent result there. So in conclusion, Shray is helpful when you want to handle problems that are too large to fit into one physical machine. It is pretty easy to use. It acts just like OpenMP that you can watch for data parallel loops and then restrict the range. It should also be easy to integrate in compilers and other tool chains because it works with segfault, so it does not care if you call some external library on the memory. And if you want this too for your language, you can pull it from here, and I would also be interested in collaborating on that. So, are there any questions?
Questions? So I remember when I took HPC classes many years ago, that I was also taught about these ways of simulating shared memory across a cluster using virtual memory techniques. And then for reasons I don't remember, they said they didn't work very well. So can you compare the Shray approach to whatever didn't work back then 15 years ago and what you do differently?
So I think the main difference is this owner compute rule. So say you have a distributed shared memory system like Samhita, then there are nodes that are responsible for handling the memory and nodes that are responsible for doing the computations. And that means that each node has to ask the memory server, I would like to compute this cache line, and then it computes a page, sends it back to the memory server, and this memory server is responsible for handling the coherency. And this is difficult to scale, and it has a lot of overhead. And for Shray, we don't need to ask ourselves which node is responsible for what computation, because we just have a blockwise distribution of the array. So this is less flexible, like you can't write a compiler or maybe some very irregular graph algorithm this way. So that is the trade-off you make. But for many algorithms, this is sufficient.
Well, thanks for the nice talk in the first place. I wonder, did you think about comparing it to the performance of the SEC cluster backend, which is based on the same ideas?
It does not currently run.
Too bad, yeah.
So we have to try this. The main difference between this and the SEC cluster backend is that that uses a explicit index transformation on every axis. So I would expect this to be faster by a constant factor, but have similar scaling behavior, because it does not need to check on every access. The Shray version, yes. And also, I believe it's not memory scalable, because it allocates the full array in on every node. No, but actually physically. No? Okay, well. Okay, I would have to reread the paper then. But I mean, it is in a sense similar. But the main difference is that we have we don't need to change the data accesses when reading memory. Okay, maybe we can.
So when you get a seg fault, you pull in some cache size block around that region. Is that right?
Yes.
Okay. So is there a way to get control over the batch size of how much? Is it just the cache line option to control how much you read from another space? Because I would imagine that is critical to optimizing some of these, is being able to prefetch data of a very specific size.
So it has to be a multiple of the system page size, which is 4069 bytes on most systems, because that is the granularity that the MMU works at. Other than that, you can take any multiple of this. At the moment, it is implemented with a global environment variable, but there's no reason you couldn't do this on an array basis. Is that? Yep.
I have a question.
Okay, yeah.
When you pull in the cache, how do you then save it? Because you don't keep the full array, do you then save it, allocate more space for that, or?
So we just set the memory protection to read only whenever we pull in an element. And then we can read and write to it. We don't have to copy it. And if we want to get rid of it, then we unmap it and remap it again. And the way Unix system works, because they allocate lazily, then it gets kind of kicked out of RAM.
Can the ownership is the ownership supported over a partitioning on block tiles? Let's say rectangular tiles. I would like to give this ownership to
So it is always one-dimensional. So you can, if you have a square, you cannot do it like this.
Okay, so you cannot block it.
Well, you cannot do this if you view the array as a 2D row major thing. So instead, what you would do is you would view it as a 3-dimensional or 4-dimensional array of the smaller block pieces, so that the linearization looks something like, you know, the Morton order thing, and then you can do it, but it requires a little bit of work. So I think
and overhead, because you have to. I imagine it resides somewhere, so this would be a whole operation that you have to do all over the cluster, and it's kind of a.
No,
you will have to communicate, right?
No, it's more of a conceptual difference. Like, you store your data as a higher dimensional array. So in memory, it looks the same as for MPI. It's still just contiguous in memory. It's just that your indexing looks different. So depending on the exact benchmark and if the array language can optimize your array access way, that may give some overhead, but no communication things.
I guess, yeah, thanks very much. Let's thank the speaker again, please. I think